All right, great. Hopefully that's better. Can everybody hear me well in the back? All right, awesome. So it's always hard going last in a panel of 4, so I'm going to ask 2 really quick questions. So how many people here, and I think this is going to be an increasing order, but I want to confirm. How many people are here from commercial end users? So if you work at a company that uses HPC, all right, great. Now, how many of you are from public sector end users? If you raise your hands. All right. And how many, like me, are vendors or essentially potential partners of Cycle? All right, there we go. All right, so now I've got the skew of the audience. This is great. So you're going to miss the bottom of my slides. It looks like it's completely fine. If you have any questions, feel free to raise your hand. The goal of my talk today is to give you an insight and hopefully have you end this presentation with the same understanding of the benefits of complementing internal hardware with external capacity, like Dave Pellerin and Tejas have just talked about, in servicing users. So we've been doing this a very long time. Cycle predates cloud. Got my first AWS account in 2007, and we had a production user using a mix of internal and external capacity in early 2008. So we are the leader in running cloud HPC for simulation, batch, you name it. I'll talk about a lot of use cases today, but most often I like to start with what our belief system is. And this is that, it actually echoes a lot of what Jetstream was talking about, that for us, we believe that increased access to compute creates new science. It essentially allows us to do things we could never do before, and this is actually really critical. Cloud is a way to do that, and we essentially try to build software that bridges internal and external environments and makes it so that people can control multiple users running multiple applications. All right, so this is our belief system. This is the users in the market. So for those of you that are out there thinking people are swiping their credit card and doing small spend on external cloud, most of our customer base is spending $10,000 a month all the way up to $250,000 a month. And actually, I think we have a user that's over that, but I don't know if I'm allowed to publicly disclose the number. So from a practical standpoint, this is real production usage. These are people spinning up potentially very large environments, although most of our customers are using between 100 cores and 6,400 cores. From a practical standpoint, we manage about 1 billion hours of computing now. This graph is old, for lack of a better phrase, so it's in 2014. We double about every year, so it's a 5x increase every 18 to 24 months for us. And largely, we're servicing Global 2000 customers. So from a practical standpoint, our vantage point is that we can severely impact simulation, we can severely impact batch by augmenting internal capacity with external capacity. And the way we do that is essentially freeing up internal hardware to do the stuff it's great at and using external capacity to do the stuff that it's great at in a way that's flexible for users. And that's the fundamental idea behind what we do. We do it for a number of different workloads. This is everything from financial batch to IoT processing, big data, analytics, machine learning, life sciences batch, traditional simulation, manufacturing, oil and gas, et cetera. So we'll go through case studies in each of these 4 areas. I'm going to actually walk through all of the points about managing large production workloads on cloud in the context of user examples. And we have a lot of people that have gone public and talked about what they're doing. So thankfully, I don't have to kill anyone when I tell it to you. So why would you want to manage a large production cluster on external cloud? For those of you that don't like watching these presentations, this is the slide you need to see, and then you can go back to your email. So internal plus cloud basically gives you a few key points. First, 0 Q8, or at least a fixed low Q8. And it's predictable, exceptionally predictable. And what that means is that you have predictable access, which then means that people tend to work quicker. The second thing is you're no longer sizing your question to the box you have on your floor. You're sizing the infrastructure to the question. And for a lot of Monte Carlo, parameter sweep, and other workloads where scale does really give you a better answer, we're essentially able to allow users to consider any scale, any time, without having to worry about the internal infrastructure only. Next, for admins, and I've managed number 84 on a top 500 list for a Disney movie production right before starting cycle. So I was a user. I was an HPC guy that eventually did cloud. Users with unique requirements are okay. So if someone wants to run Spark and your nodes really aren't that way on your internal environment, or they want to run a mixture of Kafka and a Cassandra backend and a few other things that don't really fit into your infrastructure, that's fine. Put them over here. Like, that's a totally okay thing to do. Yes? Sure.
Cloud benefits all make sense. What about small businesses or some others who don't have any internal resources but still need to do this kind of computing?
Yeah, we definitely, we do see the traditional Intel missing middle component in the business. We have a number of startups. So our customer base is a majority of Big 10 pharma, 3 of the 5 largest insurance, life retirement services, blocks of business, a number of the largest banks, a number of the largest hedge funds, a number of Fortune 500 manufacturing, NASA and FDA, and then startups. So there definitely are people that are in that space that either in life sciences or manufacturing would benefit. Practically speaking, though, from getting back to the impact and the access piece, we think that there's kind of a 1% phenomenon occurring in the market. So for corporate users, the top 1%, that triangle of, there's way more users at the bottom, right? There's a lot of small users, but if you look at consumption, it's an inverted triangle. The top 1%, just like in wealth, the top 1% of computing facilities are doing the vast majority of all computing, period, bar none, full stop. So in terms of benefits, just getting back to this, performance goes up over time at the same cost. There's a new model in cloud. You pay the same amount on an AWS instance. You get the CC2 instances. Then you get the C3s. Then you get the C4s. Azure does the same thing with the A9s, the A10s, et cetera. The march of progress occurs, but your dollar amount stays the same. That's a little different. Time and cost then become the sole things that you actually care about when you're running things externally. You no longer care about what the cooling you have available is, what the how you're going to get this cabled and up and running on time so that the large user can take advantage of it immediately. All of those logistical considerations are now external to your organization when it comes to extra burst capacity. This then enables you to have faster iterations, so your users get direct access to compute. They'll iterate faster, and what that generally means is that you end up with a model where every user gets their own environment, their own playground, but you're still controlling the OS, you're still controlling the VPN, you still control all aspects of it. It's single tenant, but you're able to give people their own playpen, which basically means in order for someone to win, someone else doesn't have to lose, which when you're using shared infrastructure is not the case. So from a practical standpoint, these are the benefits. I'm going to walk through all of them individually and we'll talk about them. So benefit number 1, zero queue wait for computing. So cloud's just a tool. It augments existing servers. Most of our customers are using a mix of internal capacity and external. And what this translates to is get the simple stuff off the hardware that's capable of doing the hard stuff. That's basically the way to look at this. This is a wrench, a hammer. If you have a bolt that you have to deal with, use the wrench. If you have a nail, use the hammer. This is very much orientated around throughput computing. It's an opportunity to free up the Maserati to do the stuff the Maserati is really good at and use the school bus to do the stuff that the school bus is really good at. So a user that used this exact model and talked, I believe, at Amazon reInvent, and now they're using various sources of capacity. They essentially have internally a job broker through Cycle that allows them to either use an internal cluster or be able to take advantage of an external cluster in a number of different models. And that's really solving, again, just the peak versus median usage size. Fixed size clusters, when we were at the movie, at the beginning of the movie, we had way too much compute. At the end of the movie, we had way too little. It was the wrong size literally all the time. The internal fixed environment was just limiting in that respect. It had awesome performance. If we could have dipped in at the end of the production and grabbed compute capacity from Amazon or Microsoft or Google and used that to run basically renders that had to finish by end of day, it would have been transformative for us as a movie production facility. So this is really the problem that we're solving. Benefit number 2, any scale at any time. So you've got an internal footprint that you could afford to purchase and essentially run with whatever technology bets and decisions you had to make. When you use external capacity, this use case for Novartis got mentioned, I think, by Dave Pellerin. They had about 341,000 hours. That's the equivalent of 40 years of computing on a single core. They ran it in 9 by spinning up a 10,000 server environment. So this got done across multiple AZs in multiple regions. Our software can do this in a matter of minutes. Their internal environment got completely unaffected. Their queue wait time internally was not extended because of this user that had a special cancer target match locking key style docking problem. They were instead able to run this workload. It used about 4 terabytes of molecular data, so we essentially have 3 pieces of software that we do. We do the workload placement and burst piece, the orchestration of the compute environments, and then the data workflow to make sure the data is in the right place at the right time for the operations. We're also optimizing in the background for things like spot instances if they're available, and doing application-aware orchestration, so we're creating the right nodes for the right applications. This is a classic example of burst capacity that enables you to do a scale you would not have been able to do in-house. It ran a workload about 180 days faster than if they had carved off 5% of their cluster and denied it to other internal users. And this was a clear success. They basically found 3 compounds that they would not have found otherwise. Another example of this is a workload that we did with the Broad Institute, which is a large genomic processing center outside of Cambridge, Massachusetts, and essentially they had a set of public data sets that they manage around cell lines and small molecules and various metadata around research papers, and they wanted to use machine learning to try to determine the interrelationships so that if you're a researcher and you're working on this cancer target, you know that you should be looking at these data sets or these other cancer targets because they statistically appear to be related. So that's what the problem that this was solving. We got them up and running on 8,000 cores in an hour and 15 minutes, and then got it on 51,000 cores in about 2 weeks, just moving some application kinks from the architecture. They ran 30 years of computing in 6 hours. It cost a few $1,000, and essentially they had an exceptionally successful run using the Google equivalent of spot instances, which is called preemptible instances. So benefit 3, users with unique requirements are okay. So you have 2 forms of challenge when you're managing a homogeneous cluster. One is the software implications. The other is the hardware implications. Both of these can be changed, and you can run this as a separate environment and get access to it in 15 minutes in external capacity without having to change your internal compute footprint. Now, most orgs, when they're doing a cluster, they're using some choice in this matrix of how are we going to deal with scheduling? How are we going to deal with administration? How are we going to deal with OS deployment and app deployment? How are we going to deal with the file system layer, et cetera? We support all of these choices and have several defaults around encryption, like in our orchestration framework. And if a user decides that they have a different choice here than your main cluster does, that's totally okay. You can run them externally. This is not something where it has to interrupt your administration of the cluster. It doesn't have to make the job challenging. And that's a model difference and a benefit we definitely see with customers. An example of this was NASA. They had a research workload to try and calculate the exact number of bushes and trees that are present in sub-Saharan Africa, which is really cool. But from a practical standpoint, that workload did not fit well on their internal environment. The internal environment was fully busy. The node profile didn't match the workload profile and would have been highly inefficient for them to run. So they basically have been putting off this researcher. Instead, they pointed them at AWS. We ran a workflow that basically, as the data came out of the satellite and plopped down on local disk, the workflow engine uploaded the data into Amazon S3, spun up clusters to run the workload alongside it, transferred the data back, and basically plopped it down like it was already run locally. It was no difference from the end user's perspective as though it had run on an internal kit. And this enabled them to enable a workload that they just were never running. They had been putting off the researcher. It allowed them to do something that they couldn't have done otherwise. As to operations, I guess, this is the kind of thing where you can get real benefit out of external capacity, is when it simplifies your internal management of your internal cluster. Another example is LifeTech, which is now part of Thermo Fisher, gave a talk on Ion Torrent, which is the best-selling mid-range genomic sequencer. It's a $50,000 box that allows you to sequence genomes. They use AWS at the time that they gave this presentation. They were using CC2 instances and CycleCloud to run a Hadoop cluster. They then later switched that over to a batch environment running Grid Engine. These users essentially had different versions of this software, had different requirements, and they didn't have to interrupt production in order to be able to deploy the new version, fully vet it, and then switch over to the new version. So this is an exciting example of being able to use a tool chain that's different than what you're using before without having to interrupt production. Benefit number 4, performance goes up over time at the same cost. So this is a tricky one. It's one that didn't dawn on us for a little while, like 2011. And it took us years of working with this stuff to realize how important this is. So I can't underline this one enough. So you used to have one update every 3 years with your kit if you were depreciating on a 3-year schedule. So you buy the hardware, you install it. When we did this at the movie, we depreciated, I think actually in that industry, over 4. But either way, per depreciated dollar, I got the same amount of compute over that time frame. When you're dealing with external capacity, that is no longer the case, even in one provider. So Tejas and Dave are updating their equipment all the time. Not only that, there's 3 at-scale public clouds. That means you're getting 3 bites at the apple a year rather than 1 every 3 years. For the same dollar amount, you get more compute. So this takes, for example, EDA licenses. Always makes sense to buy hardware initially on an EDA license because the kit you get directly from a hardware manufacturer is going to be faster than whatever instance was rolled out a year ago at scale inside of a cloud. 6 months from now, not the case. So there's a real challenge around managing compute over time. This is a tool and a benefit that we see G2000 at-scale users. This is why you're spending $250,000 a month on external compute capacity. And obviously, at that point, it's important to have optimal application deployment, financial controls, so that you can have multiple users using multiple of these applications on a mix of internal and external, and be able to reconcile budgets, and essentially enable consistent maintenance across the internal and the external environments, and that's what we do. So again, many updates per provider per year. What you really want is the ability to deploy an application consistently between internal and the 3 different providers. And what this then means is that benchmarking is a moving target. So performance application benchmarking is no longer I'll get HP and Dell and IBM. What you really want is you want to buy a rack from Dell and then be able to burst when certain applications make more sense externally or more sense internally, depending on the footprint of the workload. An example of this is HCST. They have an at-scale workload that I'll talk about later. But one of the things that they're doing is they use a tremendous amount of AWS on a regular basis, all the time. They also have benchmarked and are essentially using other providers where it's applicable, because applications will go through life cycles where, for example, Fluent makes a lot of sense on AWS. It makes a lot of sense on Azure. It depends on the detail of how you use Fluent as to where the right place to run it is. RDMA, obviously the Linux RDMA talk that Tejas gave earlier, has tremendously good performance characteristics. The bidirectional networking that AWS does has similar characteristics. From a practical standpoint, it's important to be able to look at each of the different environments, understand for these applications, this is the fastest way to run the workload or the cheapest way to run the workload when I do go to run it externally. The other thing this means is that you want your tools, even if you're rolling your own, if you're writing your own, regardless of whether or not you use Cycle, we don't make sense for everybody, but from a practical standpoint, you want to be able to visualize both the data and the compute aspect of a large cluster in both contexts across different providers. Number 5, so you no longer care about a lot of stuff. Time and compute are the only thing you care about when you're actually bursting externally. So if you have really tuned workloads running on your internal kit and someone wants to run Blast on it, you can move Blast externally, but when you do that, you no longer care about how much power you have, how much cooling you have. I mean, just think of all the things you don't have to care about in that example. There's just, how many people here have cabled anything? I have. It sucks. So an example of this is a large financial services use case, had a regulatory workload. Initially, I think it was spec'd out at 500,000 hours, but I think if I'm not mistaken, it's about 250,000 hours to run this regulatory workload. They did not have time in between when the workload was due with the regulators to actually go buy the extra kit that they needed to run the workload. So this was essentially a 2,500 core internal cluster, wanted an extra 10,000 cores externally, and basically twice a year are bursting. Once we got this up into production, twice a year became month end, and month end became once or twice a week. So from a practical standpoint, again, very high burst. So you have your steady state on internal kit, and you have your external running burst workload. But tactically speaking, it's a capability that wouldn't allow you to do this use case, period, going if you didn't have access to external capacity. It just would not have been economically sensible. Number 6, so faster iterations. This is another one, actually, I'm just going to underline in big bold letters. Takes a while to realize this. Absolutely, absolutely one of the best possible benefits you can get out of this. And I'll get to it in a little bit more in the next point as well. So, HGST, we originally did it on 70,000 cores. They later went up to 85,000. Dave Pellerin was kind enough to mention this use case. Deferred a $30 million internal spend, which they never would have done anyway. This is a workload to design heads. So essentially, it's a needle in a haystack. So you have 1 million different possible combinations of material on the surface of the disk. The materials that are layered, there's about 6 of them, so there's a combinatorial factor there, and the angle at which the head is resting relative to the plate itself. So between that, there was essentially rounding a little over 1 million possible permutations. They wanted to do all of them. They never had been doing that. In the past, they had essentially been running on a few hundred cores in-house. So we spun up a 70,000 core environment. We got this 90x faster runtime, essentially in 9 hours, ran about 70 years of simulation on spot instances, and it was $9,000. So it's as though you took a server and a half and bled out all the core hours it was ever going to produce in its lifetime of 3 years of depreciation in a 9-hour window and got an answer back at cost. That's literally what's going on. So these are slides given by someone in that organization around what they thought was going to happen relative to this class of workload. So the original thought process was you do a month of analysis, a month of simulation, a month of analysis, a month of simulation. That's your iteration time. So if you spin up the computing, you're going to do a month of analysis and 8 hours of simulation, a month of analysis, 8 hours of simulation. But that's not what actually happens. So if you look at the number of hamburgers we made in the 1800s versus post-McDonald's, when you can do something faster and it's easier, you do it more. So what happened here is the exact same situation. We essentially saw the iteration time go down from 2 months to 3 days, where you're doing a day of computing, 2 days of analysis, no context switching, no what was I asking when I did this? Let me look at my notes. Let me get my head in the right frame of mind again, et cetera. We expect similar changes to occur when 2 days or 1 day of computing goes to an hour. So we're not at the end of this yet. We're in the middle. But as this gets more interactive, it's going to get harder. Everything's going to get burstier and burstier for throughput-oriented problems. It's just the way of the world. So what this means is that we can build very large environments to support faster answers. And I know someone asked a question about the 156,000 core run. After I'm done talking about it, if you want to raise your hand now and ask a question about it, I'm happy to take it. So we spun up essentially a large-scale environment that was using 8 public regions of AWS. It had multiple AZs per region. We were using Spot. We, on a test run of this, we ran 125,000 cores and had it up in about an hour, a little less than an hour. So if you can imagine like racking, stacking, cabling 125,000 cores in an hour, that's the equivalent of kind of what was going on here. This is, again, a throughput machine. So our peak was we actually asked the user if it was OK if we did a little Intel benchmark on each node as it came up, and then we summed them. So this isn't really our peak because it's not theoretical peak. It's also not really our max. It's kind of like a weird half cousin where we our max each box individually and then add them all together. But let's just call it our peak. So this was a 1.21 petaflop general purpose CPU machine. We ran, and I'll use a new phrase that you probably haven't heard before. We ran a quarter of a compute millennium in less than a day. So the US was younger than this would have been on one core, and we ran it in 18 hours. Total cost was $33,000. Buying a machine at this scale, I think at the time we ran this, it was like $400 a core on average, thereabouts. This was just a year and a half ago. We used a set of software, so we have a very high-scale orchestrator. We ran about 17,000 servers off of CycleCloud. We have a task distribution mechanism that we're actually going to commercialize in Q3 of this year. We're doing a lot in financial services with it. It's not a scheduler. It merely gets the work to the right place at the right time. It's double chaos, monkey, chimp, gorilla proof. So you can kill any 2 servers, AZs, or regions. And in fact, we did. As we were running this live, we essentially had a very large issue in one of the regions where we weren't getting the price we were expecting or wanted out of Spot, so the software shut down that region. We also learned not to do massive numbers of list operations against S3 in Brazil, which ended up with Brazil getting shut down by the software, and yet all the work still completed across all the other regions. So lesson number 7, and I'm going to go probably a minute over because we started a little late on mine. Every researcher gets their own toy. This is a really important one. Follow on to that. So the old way, in order for somebody to win, someone else has to lose. So take your internal infrastructure, add cloud. That's no longer the case. There is no longer okay, we got to give everything to this guy, and you're starved. That no longer occurs. So from a tactical standpoint, this means no trampling. And what we've seen in large scale at G2000 kind of companies is when you have multiple users and you're running multiple apps and you still have a single tenant, I need security, I need my own OS, I need my app stack, I need my license with my application, et cetera, there is a significant advantage to being able to give users their own environment that basically has no trampling associated with it. There's no competition for access to the resources. And what that means is that you essentially get users operating at a faster iteration cycle, which means you get, Western Digital has talked publicly at a cloud conference about the fact that they design hard drives twice as fast now because they connect users to whichever infrastructure makes the most sense and just get the job done. So individual environments increases productivity, accelerating the answer accelerates the people, which is really the point. The thing we're all bottlenecked on are budget dollars and brains. Those are the 2 things that everyone is really bottlenecked on. You shouldn't be worrying about do you have enough cooling when you're trying to solve a user's problem. And in review, these are all the benefits. This is what our user base sees. And if any of this resonated with you, Rick, I don't know where you are, but raise your hand in the back. And myself are available for questions. I have to fly out tonight, but I'd be happy to answer any questions that you have now or talk to you after the session. And this is not going to go on the public deck, but there's my email address if you want to reach out.